Let's go to the composition of the blood next, because this is an area that we're going to look at again and again. If we look at the whole composition of the body's fluids, we look at the total body weight, and about 92% of this total body weight is fluid and other tissues, bone, muscle, so on. But remember that most of the tissues themselves, other than bone, are mostly water. Muscle is mostly water. The liver is mostly water. These tissues are very, very wet. If you look at the whole blood, it's about 8%. If we take just the whole blood and ignore the rest of the water, we look at the plasma, we said that was 55%, and it broke down into mostly water. 95% is water. You have dissolved solutes in waste products, such as ions like sodium, potassium, urea, things we want to get rid of, such as urea. And then the proteins, which are 7%, and they constitute albumin, which is very important, building block, the globulins, which are very important for the immune system, fibrinogen, which is a clotting factor, and then some others. The other solutes, as I mentioned, are electrolytes, gases, some of the nutrients, and other signalers, regulatory substances, which I won't talk about now. This brings us back to this important 45%, which are the formed blood elements. Now, we're going to look at this in more detail, but basically we have white cells called leukocytes. Leuko means white. Red cells, erythrocytes. And then we have some things called platelets, which are here, look like little shattered, broken dishes. That's exactly how they got their name. Here in the breakdown, these run in normal ranges of 4 to 5 million in a cc of blood. The white cells are 5 to 10,000. Somebody with leukemia, white blood, may have 100, 200, 400,000 white cells. And they happen to be bad white cells because they're malignant. I'll talk to you about those at some time later. And then the platelets, which are somewhere in this range of 250,000 to 400,000 in a cc of blood, and that's a lot. And they look like the little broken particles. And then there's a further breakdown of the kinds of white cells that I won't dwell on now because we're going to go into those one by one a little later. The erythrocytes basically capture and hold oxygen in the hemoglobin molecule, and then they release that oxygen when they get to the tissues. They then pick up carbon dioxide, bring that out to the lungs for excretion. The erythrocyte looks like this. There it is, showing it at 8 microns in diameter, and it's a biconcave disc. And if you look at this shape, the reason the shape evolved is that it's very good for the exchange of gases. If it were a ball, it would also be good for the exchange of gases, but it would take up too much room. So what evolution did was it got rid of its nucleus, and it just made it pure hemoglobin inside this disc. This disc can also fold. A ball can't fold, and it can get through narrow spaces sometimes. And when the red blood cells are actually first formed in the system, and we turn over our red blood cells about every 120 days, they actually have a little nucleus. And we can tell if somebody is anemic or fighting an anemia by seeing too many nucleated red blood cells in the blood, because those should go away. Those are the immature forms. If you go to much, much greater magnification, you look at the hemoglobin molecule inside the red cell, it looks something like this. And this little disc is its iron base. Fe is the chemical symbol for iron, ferrous or ferric, and it is an iron-based molecule with nitrogen and carbon and hydrogen, which is what most biologic systems contain. Now, there's a lot of these molecules in hemoglobin. In every red cell, there's about 300 million of these. There's a lot of oxygen-carrying capacity in them. And they have a very high affinity for oxygen. And the affinity is pH-based. Now, they also have a certain affinity for the carbon dioxide, and it's a beautiful system because what happens in this system is that different pHs occur in different parts of the system, of the cardiovascular system, favoring the release or the retention of oxygen and carbon dioxide. So when you have blood with oxygen on it, the hemoglobin with its attached oxygen molecules coming to the tissues, the pH at the tissue level is just right for the release of the carbon dioxide and the retention, of the oxygen into the tissues and the retention of the waste carbon dioxide. When it gets back out to the lungs, the pH changes slightly. And this complex molecule favors the absorption of oxygen and the release of carbon dioxide. It's an absolutely beautiful, beautiful system. There are some problems, and we always get into the problems here. There's another molecule that looks very much like carbon dioxide, and it's called carbon monoxide. In our world, incomplete combustion results in carbon monoxide both in the atmosphere, in artificial products, and also in our body. If you look at this slide, when you combine a hydrocarbon, this is hydrogen and carbon, and I have it in quotes because it's in varying combinations throughout our body. Almost all of our body are some combinations of hydrogen and carbon. That's organic chemistry, organic material. When it burns in the flame of combustion with oxygen, oxygen supports combustion, the product is usually carbon dioxide and water. We can deal with the water, we can deal with the carbon dioxide, 2 oxygens. But in situations of incomplete combustion, for example, if you burn your improperly ventilated stove indoors, you will release with wood, which is also hydrogen and carbon, carbon monoxide. It doesn't have enough oxygen for the complete combustion. Badly tuned carburetors in cars, bad wood stoves, all sorts of sources for carbon monoxide in our environment. It happens that carbon monoxide is drawn and held by hemoglobin at 200 times greater affinity than oxygen. So if you fall asleep in your car or in your bedroom with a badly ventilated heater, charcoal stove, you start breathing carbon monoxide, it will attach to the hemoglobin and it won't let go. And it'll get to the body tissues and it won't let go, and it'll stay in the circulation. And this is why people suffocate with carbon monoxide poisoning. They also look like they're breathing pretty well because their face is flushed. They have this cherry red skin appearance because carbon monoxide, when attached to hemoglobin, doesn't look bright red the way our oxygenated blood does, and it doesn't look bluish purple the way venous blood does. It looks cherry red. So it fools you for a minute when you see somebody in this condition. And what we do to cure this problem is we give the patient as much 100% oxygen as we can and try to force the equation, the chemical equation, by overloading the system with oxygen. You breathe in the air about 21% oxygen. And we force this to 100%, and we can force the equation. So if you can get the patient before they've had brain damage, then you can force the carbon monoxide off the molecule and replace it with oxygen. And that's what you do. You take the patient out of the room, put them in the air, and get them oxygen as soon as possible. That's the function of the red blood cell. And as I said, it has a very rapid turnover. You have a whole new system of blood in your body for the red cells about every 120 days, made in the bone marrow and then released into the circulation.